Okay, today we're going to start a new unit of circular motion and gravitation, because they are very closely related to each other. But to start with, we need to talk about a definition that we covered a long time ago, but we need to rediscover it now, and that is average speed. And when we talk about average speed, we're not talking about the change in displacement of something. We're actually talking about the total distance that someone covers over a total amount of time. It's the more intuitive version of speed and velocity. And it's basically this. It's the distance. It's the distance traveled divided by the time. And that's it. So it's d over t. But if we're dealing with a circle, okay, then, and if we complete a circle in a certain amount of time, if we go around the circle in a certain amount of time, what is the average speed? Well, we take our circle, and it has a radius r, because that's the fundamental constant for any kind of circle, and we know that the distance all the way around the circle is its circumference. And so if we're traveling around a circle, it's the circumference divided by the time for one cycle. And this is going to equal 2 pi r divided by the total amount of time. Now, we will find out that the time it takes to complete a cycle of something, this is called the period. Okay, and this is the amount of time it takes to complete one complete cycle, either around a circle or for a wave or something like that. It's a very powerful concept. Okay. However, we also need to address what the actual velocity is. Okay, and by this equals v, and we don't put a bar over this. Okay, this is just for the speed. But there is a velocity when it comes to a circle. And what we do with that, and so we're going to look at this diagram here to show the proof of how we actually get or how we determine our velocity, or we can examine our velocities in a circle, and what happens when we change our velocity. All right, so let's say we're starting here at point A, and we have this initial velocity pointing in that direction. Okay, so that'll be our VI, our initial velocity, and then we travel to point B, and as we travel to point B, if we're traveling in a circle, then our direction has changed, because at that particular moment, we're traveling that way, and we are always going to be, our velocity vector is always, as long as we are traveling at a constant speed, our velocity vector is always going to be, is tangent to the circle. Okay, at our particular point. So it's always, velocity vector is always going to be tangent to the circle at the point that we are. And just so you guys remember that here's for tangent stuff, we have, if that's going to be our radius, that this will always be a right angle. All right, so the tangent to the circle is always perpendicular to the radius of the circle. All right, so but we knew two things about velocity, and so that's our velocity. This brings us to our acceleration, and acceleration for a circle, okay, can have two things. It can either have a change in the speed, okay. Well, actually, before we go into that, let's think of it like this. Acceleration is the rate of change of velocity divided by our change in time. Okay, but velocity requires two components. It requires a speed and it requires a direction. Okay, normal acceleration, the way we've dealt with it, is we measure the rate of change of the speed of something divided by time, and that gives us our acceleration. But in this particular case, we're traveling in a circle at a constant speed. So the other thing is changing. The direction is constantly changing as you're traveling in a circle, and we can measure this rate. Okay, so what happens is we actually have the rate of change of direction over time. And that's what we're analyzing up here. That if that our delta velocity equals our final velocity minus our initial velocity. So up here we have a vector. Okay, this is our final velocity, and this is our initial velocity. Final velocity and initial velocity. And if we subtract them, okay, remember that we have remember that our there we go. That's v final, and to subtract something, you add the negative vector. So it's going to be, if vf minus vi is this, then it's going to be vf plus a negative vi. Well, negative vi is just this horizontal, but it's in the opposite direction. Okay, well, look at the vector that gives us. That's going to give us, because if we're adding them, it's going to give us this vector. Well, where does that go? Look at the direction where that points if this is measured from point B. If that's point B right there, okay, so that's point B. Okay, look at that angle there. Okay, that looks an awful lot like a right angle. Okay, and if that's the case, then our velocity vector, our acceleration vector, is pointed at the center of the circle. In which case, if we have a center directed vector, it is called centripetal. Okay? And so whenever we're traveling in a circle, our acceleration is always changing our velocity back towards the center of the circle. It is called a centripetal acceleration. And whenever you have an acceleration, what things cause centripetal accelerations? They must be centripetal forces. Centripetal forces cause centripetal accelerations. All right, so right here we're going to take a break, or take a break from this, and I want you to look at a visual proof of something being a centripetal acceleration, or actually how this could possibly be where if it feels like we should be pushing to the outside, the acceleration might actually be to the inside. So I'd like you guys to look at the cork in the middle of this 2-liter bottle when he spins around. Normally you would think that the cork would float to the outside, because when we spin things around, they move to the outside. But where's the cork? The cork is actually moved towards the center of the circle. And I can explain why after the video. But if the cork is moving towards the center of the video, that means the force is pushing it towards the inside, which must make it a centripetal force. And so the reason I told you the cork, or the reason why the cork was moving towards the outside, is because corks are buoyant, right? Notice that the cork was floating in the 2-liter bottle, and it had a string tied to it, keeping it down. Well, if there wasn't a string and there was no water, the cork would sink, right? Which means if gravity was working on it, because that would be the acceleration of gravity, but it's not. In fact, the cork was wanting to float to the top of the water, and that is a buoyancy issue. And so if the cork is in the water, it is going to move in the direction of the force that's acting on it. And so if it's going to float, it's going to go up. Well, if we move the water, the cork is going to go in the opposite direction of the water due to buoyancy issues. That it's not just going to move with the water. If the water moves, the cork's going to move in the opposite direction. And so that creates this weird-looking event where the cork moves towards the center when you are when we're spinning that bottle. The water actually does tend to move towards the outside, but the cork will float towards the middle. The last thing we need to talk about, though, is we have our what the equation for this is. And so the equation for the acceleration in a circle is given by v squared over r. And that's the speed of your object squared divided by the radius gives you your centripetal acceleration. And that's where we're going to stop for today.